Now I introduce the important sample the policy search. This is part one. To use the policy gradient method to run a policy to control a robot, we need to first define an objective function and then calculate his gradient. Let's start from a total return along a trajectory, which can be expressed as an integral. Here, pi is the policy, theta is the policy parameters, r is the reward. So the gradient of the objective function can be estimated along a trajectory. It's here. Because the r is not function for parameters theta, so we can move out of this gradient operator. To use the gradient method to through maximum likelihood estimate to find the optimal policy. Right now, the problem is how can we calculate this gradient of the policy? Because the policy is what we are looking for now. The goal of likelihood ratio trick is to convert the gradient of the policy to a summation over samples drawing from the policy pi. So we use the ratio trick here, this formulation, and then the gradient above we can rewrite in this formulation by using this ratio trick. I replace this term by these two terms. However, we don't want to directly calculate this integral because it's too complicated. We like to use the Monte Carlo approximation and change this, change this integral to a expectation over the samples generated under the policy pi. In this this expectation, and then can write in the sampling summation. This samples is from distribution pi, or from the distribution generated by under the policy pi. So the likelihood ratio trick simplifies the gradient calculation to the sampling summation over samples generated by under the policy pi. So through the likelihood ratio trick, we don't need we calculate the gradient of the policy. Instead, we calculate the sampling summation. However, because the policy pi is we are looking for, we are searching for, so we cannot use it to generate samples to searching for the policy itself. So we need a method like importance sampling to calculate the expectation over the p over the pi, for example. Use the sampling from different distribution Q. Let's say original problem is we need the calculate the expectation of the function f over the distribution p. And then what we can do by using the importance sampling, we move this function p inside the square brackets. And then we times p use q times denominator and put q in the denominator because it's cancel each other is 1, the same as this one. Then now, because this q is a different distribution, we move this q to the to here. That means we sample all the variable x from this different distribution q, not from the original distribution p. In this way, we change the samples from Q, not from P. Then we use we can say same way we get the sampling summation differences. This X, this samples, this from Q, not from P. If this Z denominator is same as equal to M, then important sampling is unbiased. However, right now we select the P in this summation to provide lower covariance. So right now, we are using off policy sample from the distribution Q, not from the original distribution P. That's back to the original problem. We can calculate the objective function of the expectation of the objective function over P. P is a different distribution. And then we can express it as a sampling summation over the P. This she is sampled from a distribution Q, not from the policy pi. Since the path reward do not depend on the future action, so for this each reward at T, we only use the policy before this current time T. So that means we if, for example, for the robot problem, we know the system dynamic approximation, so we can tentatively optimize this system dynamic, and then we optimize the policy pi. Finally, we get the optimal pi. For more detailed policy search, please watch the part 2. For more details, please check with this reference. Thank you. Bye.